Good morning, everyone. We'll start in a couple of minutes. If you're here, I'm just trying to find my glasses, as always, and then we'll get started. Remember to stick in the chat where you're from as well. I always love seeing where everybody's sitting in the morning on a Saturday morning from. Hey everyone, hopefully everyone can hear me okay. Me trying to check my mic was working. I managed to destroy my settings about 5 minutes ago. Still trying to learn what to do. So if you can hear me, it would be great if you could just drop something in the chat just so I can see what's going on. Yeah, we've got someone waving, that's cool. Yeah, we're all good. Right then, so how's everyone doing this morning? It's an early one today. I'm trying to fit the live sessions into trying to do so many other things. As always, you know, family and work and trying to get around and all that type of stuff. So I think what we'll do moving forward is try to do them around this time of the day. It's sort of early enough in the UK, but not too late elsewhere. Yeah, so we'll give it a go and we'll see how many people turn out and how many people get something from it. But remember, you can always come back to this recording later on. That's the whole point of this. Today's session, we're going to go through the practical part. I still get an awful lot of questions on the practical, but our next session, we will be doing the WPS. Yeah, so the welder quals, welding procedures, the questions around that, how it's laid out. I am busy building a load of sort of interactive questions for us to go through together on that side, because there's a lot I want to try and cover as much as possible. Okay, so we'll give this a go. We'll see how it works. Again, working with these samples, I would have them in your hand if we were in a room. We're not all together, of course, so we'll see how it works and away we go. The biggest part of this is how many questions you guys ask, okay? Let's keep it to the practical session today, just so we can try and stay a little bit focused. But if you've got a question, ask it, we'll move on, okay? And what's already getting on my nerves is I'm going to remove that logo, hopefully, so only one of them appears on the screen, right? Hopefully that works, and we'll see how we get on. Right, so I should be able to jump across here. Good morning, everyone. Sorry, Chris, Lex. Yeah, good morning, everyone. Right. Ooh, not that screen. That's not the screen I want to show you. That's my streaming screen. Will that come up here? There we go. First thing for us to capture. Let me make sure I can see the chat as well, because there's too many things to do. There we go. Right. The first thing we need to make sure we cover is what the requirements for this practical session are. There's the exam is used in two different versions of CSWIP, in your 3.0 and your 3.1. Okay, it's the same practical now. For the plate, if you're doing a 3.0, you'll also do a fillet weld, but if you're doing a 3.1, you'll just do these 8 segments, right? So again, I keep trying to point everybody to this document. You can go on Google and just type in CSWIP WI-692. This is the scheme document that tells you everything you need to know about your qualification, your entry requirements, your examination, your renewal, all that type of thing, okay? a lot of questions are answered in that document, but this is where it tells us what the practical is, right? So there is 2 parts to this, right? We've got our 3.0, which is our visual weld inspector. Now, unfortunately, in this document, they don't term things 3.0, 3.1, 3.2. They call it visual weld inspector, and senior weld inspector, okay? So we've got our 3.0 there, and then we've got our requirements for our 3.1. So if we go to those sections, the references, those appendixes, we get this for the 3.0. So you have 2 parts. 3.0 is just practical completely, and you get a practical part A and a practical part B, which is your 8 segments and your fillet. You get 90 minutes for your plate segments, which is what we're going to cover today. And then if you're in your 3.1, you're going to get 3 parts. So you've got your theory, your 80 questions, leading, all that type of thing. Then you've got your weld equals and weld procedures. And then we have there our 8 segments. Now, for some reason, they say 90 minutes in the 3.0 and then 1 hour 30 minutes for the 3.1, but they're the same. Yeah, 90 minutes should be easily enough time for us to complete these exams. Okay. If you're taking longer than that or anywhere near that, you are looking in too much depth, and we need to work on the speed in which you're going through this. I honestly think this exam should take you 8 segments with the acceptance about 45 to 50 minutes. Okay. And that's what we want to kind of be aiming to hit. Okay. That gives us enough time for all of this settling down at the beginning of the exam, not being rushed, not being panicked, because the more panicked we are, the more problems that's going to cost us, during making wrong decisions and stuff like that. Yeah. The exam is 70% pass mark. We can see there on the screen. And this is where the negative marking is. So we'll look later on when we look at how to fill in the answer grid. But because there's an answer grid with all the defects on, to stop you just putting an X in every single box and getting them all right, then they have to have negative marking. So negative marking works by you put 1 right answer on and 1 wrong answer on, you get 0 marks. So you take the wrong answers away from the right answers, okay? And it's really the only way that this version of the exam works, if we do that. So my first sort of thing here is only put down what you know is there. And all the defects are really, really clear, okay? There is nothing that's touch and go. We're going to see this, for example, porosity was like a really big thing for people, okay? Every time we picked up one of these samples and we were like, oh, I can see gas pores all over it. Some of them were defect marks, some of them were really there. When we look at the new acceptance criteria, porosity is not there anymore. So don't go looking for it. Only look for things which are in the acceptance criteria and are clear. I mean, I'm going to pick up one of these plates here. You probably see it on there. Does everybody see that defect here? Gives a heads up if you can. Because if you can't, you shouldn't be inspecting, right? That's how big these defects are. We can see them a mile off. Now, some of them are tiny, but in honesty, the ones which are like 1 mil, less than 1 mil, won't throw up a change in your mark, right? It's not enough to knock you out of a grouping or something like that. Okay, so anyway, that's where we get the exam requirements from. That's how you know. Now we should check this document fairly regularly, because the document does change. The CSWIP committee meet often, a couple of times a year, and they'll look at how things are working and make changes. So always keep an eye on it and see what you need to hit. Okay, next bit. What is a defect and what isn't? Terminology is really important. So our first one is the term imperfection. Now, our plates, or welds, whatever we're looking at, have lots of imperfections. This is anything that is away from perfect, right? So we're all full of imperfections. We're not all there, but they could be acceptable or rejectable. Okay, so the first thing we're going to look at when we do any inspection is what imperfections can I see. We then need to make a decision if that imperfection is acceptable or rejectable, and at that point, it becomes a defect. Right? If we reject it, if we reject the imperfection, it's a defect, right? And this becomes very weird when we communicate about defects, especially when we mix British standards or ISOs and American standards, the ASMEs. These terminologies are really important. Always read the question to what they're asking. Okay, this goes for both the practical and the theory choices. Imperfections, anything out of perfect, defects, things which are rejectable. Okay. The whole exam is based upon really ISO 5871, right? This is the European defect acceptance criteria. Has anybody seen this or used 5871 before? It gives us time to have a cup of tea if I ask a question, you see, and I can check who's still here. Yeah, 5817. It's a good standard. It's one based really on free acceptance criteria levels, yeah, and really it's one of my favorite, if that's the term for it, standards. What it allows us is to really detail every type of defect as we go down in one table, and nearly every defect is covered within 5817. But what we have is a couple of different points to it. So we've got our 6520 standard. Now, this is a standard that a lot of people don't come by very often. Okay, it's a definition standard, really, I think is the best way to say it, and it gives a bit more of an overview of when we say crack, what do we mean by a crack? When we say surface pop, what do we mean by that? So every one of them is given a number, a little serial number down the side here, which says what that is. In the majority of the time, we can ignore this section of it, right? It's additional information if we need it. We then got a description of the defects, right, which are really good if we're stuck, right? And we're going to come back to this when we look at our acceptance criteria for the exams. But remembering that the standards tend to tell you what a defect looks like. So if I don't know or I can't remember what incomplete pen looks like, at the bottom here, there's a little sketch and a description telling me, right? So I can just remind myself and do that. We've then got our 3 levels of quality limits, okay? In 5817, we have class D, C, and B. So D is like why I wouldn't even bother looking at it if it was a class D. Class C is generally okay. B is our highest level of acceptance criteria within the standard. But often a lot of client specs work to things which are like B+. So B plus additional things that tighten it up a little bit more. But we can see on the screen here, we've pretty much got level B, everything's not permitted. Level C, some things are not permitted. Level D, most things are permitted with a bit of tolerance. Okay, so if we take that standard of 5817, CSWIP have really taken the layout of this to make your exams. Okay, so to understand these, have a look. You'll see some of the equations which are in 5817 are what you need to know for CSWIP because they're just taken from there. Right. Okay, so let's start looking at the different parts of our welds and where we're likely to see issues when we do our inspection. Okay, so here's a macro section. Right? What's a macro section? It's a relatively low magnification look at the weld, normally between 2 to 10 times mag. Okay, the idea here is we're looking for welding defects in areas of that we may potentially have imperfections within. You can often see the parent material, the heat affected zone, and the weld metal, but you can't see the grain structure. Okay, that's a micro examination, and micro exams are done at much higher magnification levels, depending on the material we're doing. It could be 2,500, 3,000 times magnification. But using this macro here, we can identify a couple of different places. So in our exam, we are not going to be able to see internal defects. Yeah, so everything we're seeing are surface breaking imperfections. Right? And in the main, that's going to be on a weld toes, in the cap, and on the root. Okay. If you're trying to work through welding defects and work out what's happening and try and commit things to memory, just take all the internal defects and just get rid of them for the minute. Right, we will only see them when we come to do a macro or NDT of some type. Okay, understanding which defects are likely to appear in which area is also really important to make sure we identify our defects correctly. So things like slag, for us, are never going to occur directly down the middle of the cap of a weld. They will occur in the toes of a weld. So if you've got a single pass weld like this, okay, you will not get the weld appearing down the slag appearing down the middle. You will get it in the toes. But if you've got a weld like this, where you've got two welds coming together, yeah, I'll tell you what I'll do. I'll do this. Two welds coming together like this, then you could get slag running down the inside. Okay, so knowing the difference between these two different types of welds and where we're likely to find it will stop you getting negative marks by calling up the wrong defect. Yeah. Am I likely to see a tungsten inclusion? Okay, again, I get to take a cup of tea, have a wait. Tungsten inclusion. Are you from Asia? Where in Asia? Asia's a big place. we need a little bit more while we're waiting for people to tell me if they can find tungsten or not. Okay. Yeah, this is where it feels like I go quiet as people try to type away. Yeah. Great content, me sitting here staring at the screen waiting for someone to reply. No? If anybody's going to reply, of course, I could sit here for 5 minutes and nobody type anything. Tungsten would be within the body of the weld. Exactly. Thanks, Chris. Yes. Batam. Oh, Batam. Hey. Yes. Body of the weld. This is where we get our touchdowns. So we're going to bury the tungsten into stop starts or in it. What welding process does that appear in? And I'm asking that. I won't wait. I guess I'll wait for everybody to reply. But we've got to know the welding process. So if I said this was stick welded, SMA, W, MMA, whichever version we want to use, name, right? Am I going to find tungsten inclusion? No. Right? Yeah. Everyone's saying take. Yeah. So getting rid of that, right? I'm not looking for tungsten inclusion because I'm using a stick weld. I can forget about all them defects, right? If the welding process is stated as being MIG welding or mag welding, we'll say mag. MIG for aluminium, mag for steels. If I say mag welding, I don't have to worry about slag inclusions. We're looking for silica, right? And so understanding welding defect against welding process we need to hit as well. Yes, TIG 141 is the process number for that, and they're good to know as well for your multi-choices. Okay, so we have to hit there. So know your locations. Know your locations and what defects are likely to occur. What I often like to do is just draw a cross section of a weld like what's on the screen and just label top and bottom. What is going to happen on the cap of the weld? What is going to happen on the root? How do I know what they look like? And can I just generally find defects? Then write the welding processes down and say which welding defects are going to occur with which welding processes. So this can be easy. You know, TIG, you can say tungsten, crater cracks, you know, the other generals, but then they're the two which are process specific normally. Stick welding, stop-start porosity, poor stop-starts, really high build-ups of welds. What else? Slag inclusion, undercut from improper angle of your torch. If you can list all them down, we're halfway there. Okay. Right. Yeah. Wrong. Sorry, I'm just reading the comments as we go around, just for a stop here before we move to the next section. So we've got Pakistan, cool. Malaysia, hey Malaysia. Well, my family's Singaporean, so you know Malaysia, yay, ish. So just passed my free one inspector exam. Oh, great, thank you. That's well done, mate. Leon, that's awesome news for passing. I'm glad the videos have helped. Yeah. Sharia, yes, the next live session will be on the WPSs and welder course. Okay. Right. So let's get into defects then. So here we have our first indication, right? So, you know, I'm looking at that. I've managed to cover this. I'm just going to move myself to the side here, if I can. Right, there you go. Right. Excess weld metal is not called reinforcement. That's our first thing, okay? Excess weld metal doesn't reinforce anything. The likelihood is it's going to cause us more issues depending on how big that excess weld metal is and the torr of the weld that it produces. In general, we can say the higher the excess weld metal, the more extreme the torr blend is going to be. Okay, if we limit the excess weld metal, most standards try to limit it to like a max of 3 mil. The idea is that the torr blend will run evenly and smoothly with the base material. Okay, in 5817 and therefore within the CSWIP exams, you tend to see an equation which is like height is equal to 0.1 times B plus 1 millimeter, right? And this is where we get that from. And what it's trying to do is trying to say the wider the weld, the higher it can be. The thinner the weld, the shallower it has to be to maintain that group, right? Now, we absolutely just use our weld gauges, you know, lots of different type of weld gauge. I've got some tips on cam gauge use on the channel. Probably the most watched video, just me showing people how to use a cam gauge. But this is really important. You need to know how to zero your cam gauge and check it before you take your measurements so you know you're as accurate as possible. Okay, if your cam gauge is not zeroed correctly, all your results will be out. Okay, and we're going to be losing at least 8 marks if your gauge is out. So give that video a look. Hopefully you can scan that QR code and it should work, and we go from there. Okay, so excess weld metal, we've got to keep an eye on it. We're going to look at it, how we do that in a bit, but that's what we're looking for. Underfill and incomplete fill, right? Same thing, different term, right? This is at any point at which our weld metal falls beneath the plane of the plate each way. So you can see we've got it detailed here on the slide as an H with our dotted line. We don't have to take the depth of this. We just need to know if it's there or not. Now, one of the easiest ways to do that is to take your finger and run your hand over your sample and feel if the weld metal dips down or not. Sometimes you can see it really, really clearly. Like at the end of this sample here, again, I'll go to here. At the end of our sample here, it's underfilled. It doesn't come up and fill the joint right the way up, right? I've also got underfill here along the center of my weld. We haven't got enough weld metal, okay? So just feeling it and going, is that under the plane of the plate or not, is going to tell us if we've got underfill or incomplete fill groove, okay? Now, in a lot of circumstances, we get two defects together. Now, this is a big bone of contention with a lot of students and a lot of people who do the training and all this type of things. Why do I have to call both defects up if they're in the same location? Well, the idea here is that they've got different acceptance criteria, and the exam is not saying, would you pass or fail this weld as an entire weld? Because the answer is always going to be, it's going to fail, right? The question is, can you identify the different types of welding defects and then check them individually against a procedure? So we are always going to ask, as trainers or examiners or certifying bodies, can you see these defects, right? So in these examples I've got on the board here, right, we can see we have underfill, and because we have underfill of the sidewall, we haven't filled the joint completely up, we also have lack of sidewall fusion, right? If you only say one defect in this location, you will lose your marks, right? So when we come in, the question asks us, do we have underfill? Yes, we have underfill. Do you have lack of sidewall fusion? Yes, we have lack of sidewall fusion. But we can see, if I look at the one above here, this underfill, this one just has underfill, right? It's here, it's underfilled by itself because it's fused the sides. But this one has underfill plus lack of sidewall fusion. And we can see that all the way along in these areas, okay? Is everybody going to promise me that if they see or they tick the box that says lack of sidewall fusion, you will also tick underfill? Because you can only visually see lack of sidewall fusion, surface break and lack of sidewall, if you have underfill. They've got to go together in this case, right? So many people miss that out. Now, in reality, when we're out on a job and we're actually inspecting, are we going to do that? Probably not. We're probably just going to say lack of sidewall fusion. But for your exam, you're in an exam. You're not in the real world, right? So we've got to show we can do that. Have I harped on about that enough? Right? It's a big thing that in every course I teach, people miss it. They will say one or the other, but not both. We have to say both, okay? Because that's the point of the exam, is to identify defects, okay? If you've got any questions on that, ask, and when we have a pause and I read the comments, I'll see what there is, okay? Right. So here we've got slag inclusions. Now, slag inclusions are going to occur inside of another defect normally. Something that can hold the slag in place and push it forward. So for this, we're normally looking on the toes of the welds or somewhere we can get trapped inside. Like I said, when we look at our sample here and we've got the lack of interrun fusion, it's potentially we're going to have a load of slag running down the internals here, okay? If I was looking at this sample, right, we can sort of say, well, would I have slag coming down here? Well, yeah, look, we've got some, potentially if I can get it in the light right, this bitty material in the bottom of this weld here, you can see where it's a little bit like moving around, that's our slag. Our slag is there because it's trapped in that underfill and lacquer sidewall fusion. Okay, we haven't got it out. We're probably grinding and refilling and moving on. Okay, slag by itself generally normally has a fairly big acceptance criteria, but we don't want it, okay, because it's going to allow other defects to occur, like lack of sidewall fusion, lack of interrun fusion, and so on. Okay, right. So here's a imperfection on the screen. What do we think we've got? Right? Can you tell me how many defects there are and what they are by this picture? You know, fairly simple picture, of course, but again, I get to have a drink. And while people go to reply, I'll see if we've got any comments. No questions on lack of fusion, underfill. That's okay. Cool. See, just while people reply, Leon, if you've already passed your 3-1, you know, you can start working towards your 3-2. We're going to start doing more videos around the 3-2 soon. But also remember, we've got a lot of welding engineering videos just in general, which are always good to keep up with. So Chris has gone underfill, lack of sidewall fusion, and slag. And Danny, lack of sidewall fusion, underfill, and slag. Yeah, we've got a few here. That's great. That's right. That's what we want. Okay. So we've got 3 defects, which are going to need to be recorded separately, right, and then measured separately and accepted and rejected separately. Okay. So we get to have that. So I think I've got my underfill. Yeah. We've got a lack of sidewall fusion, and we've got a slag. And by having all 3, we know there's quite a lot of things going awry with that weld. Okay. Next one. A lot of questions around this for how we have stop starts. Stop starts is a new addition to the exam, which hasn't been there in the past. We used to just look for like where we would have porosity and stuff on a stop start, but now it's how many have we got, what position are they, what's their space, and things like that. Okay, this on the board you can see, so stop starts where we've got a weld finishing and ending and then restarting. So what makes something a good stop start or a bad stop start? And really what we're looking for is these poor stop starts. Okay, so I've tried to draw this out, so bear with me. So we've been welding along, and then we stop, and at the end of the weld we have that flat crater position, and then we restart to weld, and we come along, and we end up with something like this. Anywhere where we can see that overlap of the weld and that crater in the middle is going to be our poor stop start. Okay. So I realised in the exams there were a lot of stop starts without crater pipes or previous weld craters. Yeah. So that's what we're looking for. Do we have that? Now, how do I know that's what we're looking at in an exam? Because if we read the comments section within the acceptance criteria, it'll tell you what they're looking for. We're going to see that in a little bit when we look at the acceptance criteria. Okay. But this is what we're doing. So really what we want is to be able to weld, and then continue welding, so we lose that initial crater, so we have the overlap required. Now this is what it looks like on the cap of the weld, where if we had it on the root, what you would see is the weld coming along, and it would like sort of like thin out and then come back up again. Now where it thins out, we're likely to get other defects. So if I have this one at the top here, right, what defect is likely to be on the back side of that weld if it's a single pass weld? Okay. what do you think we're going to be looking for? As this is where we have to put the knowledge of looking at one thing and trying to work out what's on the other side of what we have. Okay. So I'm loving the amount of comments we're getting today, mind. So keep putting them in, keep asking them. Helps YouTube think I'm a decent decent channel. Yeah. Okay. Well, if I've got a poor stop start, likelihood is, yeah, like a pen. Thanks, Danny. Yeah. Right. So look at this section here. Trying to see my camera. Do you see where the weld's coming down here? If I go that way so I can see my camera a bit more. We've got this area here where we've been coming along with the weld here, and then it thins out, and we've got potentially an indication right in the middle there, and then we carry on. Okay, so it tells us that if we've got that bit at the top, we might start to have a defect on the other side. So a stop-start looks like this on the cap. It looks like this on the root. Okay, this is the areas we're looking for. I'm just trying to see if we've got one on our other sample. Not really. Okay, so stop-start. Hopefully that's okay for everyone. But yeah, lack of pen, lack of root fusion potentially on the other side, depends how much it's come through, but one of them two is more likely. So you're right, Danny. All right, our undercut. Again, another one people have a lot of questions about, because undercut says, well, there's normally quite a lot of things that will tag up if undercut is acceptable or rejectable. Really, there's are three things we're looking for. Okay, there are depth, or length, and our sharpness. Okay, now depth is really difficult to gauge normally, right? We struggle to get the end of our cam gauge into the defect, because it's normally quite thin, and the cam gauge nibs are quite large, so we don't want to rely on that at all. One way of doing it is to take our torch that you'll have in your exam. I'm going to use my mobile phone, but of course you can't have your mobile phone in the exams. And what we want to do, sorry, stop, I lose my voice a bit, is take our sample and cast the torch down the side. Now, can you see, we start to see areas of undercut depending on what we're looking at. Okay, so if I turn this one over, you see that side there is really severe, really deep undercut, but I can see it running potentially in different areas down my weld. Okay, and if I move it and I move my torch, we kind of want to do this and see if we can find different parts. Okay, now our next decision here is what is undercut and what is lacquer sidewall fusion. Okay, so undercut is normally a wavy line. Okay, we've got to decide if it's a straight line. So again, we can see here that this bottom one next to my torch, that's a straight line, but as I come up, it goes to this wavy melted line at the top. Okay, so that's my difference. I know this bit at the top is undercut, but this bit at the bottom here is a lacquer sidewall fusion because it's straight. Okay, and that's the biggest answer here. Now, the lacquer sidewall might have a slight long bending curve to it, because it might be a prep that's been hand prepped with a grinder, but it won't be jagged and running around and disappearing like we can see on our pictures here. We can see that it's not straight. That's the point of this. Okay, so use your torches, take your time, get the sample in your hands. Okay, you're going to be using the cut down samples, But get the sample in your hand, have a look around, see what it's going to be. Okay, so we're going to get that there, right? Undercut. We know the rules. We know where it's going to happen. Undercut in the main occurs within the base material. Okay. Occasionally, it could happen within the multi-run, so where it bites into the run next to it. But personally, I would just concentrate on it being in the base material. And then you don't have to try and add too much complexity to yourself. Okay? Right. How do we do depth then? Well, it's really a guess. It's kind of putting our best head on and saying, right, how deep is this undercut? Well, I'm going to say I like to use my nails. I put my nail in and go 1.5 mil, something like that, right? Let's capture it, or it's less than 0.5 mil. You know, we're not looking for desperately accurate measurements here. As long as you're right in the right ballpark, in my experience, we tend to be near enough where we need to be. Okay, and when we talk about sharpness, it's two things. It's either sharp or it's smooth. If you can get your nail in and click the defect, it's sharp. And I would say most of the defects in the world that have undercut tend to be sharp. I think if you wanted to take a guess, you're probably 99% accurate if you say sharp, you know, and we can go from there. Okay, surface porosity. Surface porosity normally occurring around the stop starts. But what we're going to see is that, and you will see within your training when you actually do your courses, that the acceptance criteria doesn't have surface porosity in it. Okay, so it's one of these defects for this exam we can forget about, but we still need to know what it is, right? So we've got generally porosity is occurring along on the stop starts of the welds. So if you've got an MMA weld and it's maybe lost a little bit of its flux when you start up, or you've had a lot of loss of gas in either TIG or MIG-MAG, that's likely where it's going to be. And the hope is that the welder starts, realizes there's no gas, and stops, and doesn't continue on like the weld we've got up on the screen here. Okay. Sometimes it's a little bit harder to see if you've got like flux core welding or something like that, where the weld might be covering up, but you can generally have a feel of it, right? And you can see it occurring as you weld them, so hopefully it gets there, right? Okay. Arc strikes, right? Hopefully everybody's been watching my video on time temperature transformation graphs. Absolutely believe that if you can nail that concept, you can understand a lot about the multi-choice questions in the exams, right? So arc strikes, always a bad thing. We tend to disallow them in pretty much all fabrication standards. In our samples, they're going to be quite large. Again, go back to this camera, like this. Okay, so we've got one area here of an arc strike. This is where we are heating the material up quite rapidly from cold, so we get above its transition temperature. We change it all up to liquid and then to austenite and fast cool it. So now it has a much higher chance of being a martensitic structure, which is more likely to break. Okay, again, we've got videos on arc strikes, identification, and cooling rates on the channel. Give that a look. Okay, we're generally going to bang these out in areas. So you see one, it's one area, 2 areas, 3 areas, whatever that be. Okay. Cracks. Now, again, we can look at our acceptance criterias and we'll see that for CSWIP, there is no acceptance criteria for cracks. so we can forget about it. Okay. Yeah, that's all we need to say about that, really. Yeah, if it's not in the acceptance criteria, we don't need to look for it. But cracks occur for a lot of different reasons. Hydrogen cracking, stress corrosion cracking, fatigue, very common in service. Okay, but yeah, we'll go from there. Okay, on to our root side then. So 3 defects, we know we have to nail on the root. If you mix these up, you're going to be dropping a lot of marks, right? The explanation of these defects is in the remarks section of the acceptance criteria. So there is no reason to miss these at all, right? But people miss them all the time. People seem to forget that there's guidance right in front of them, okay, because you don't expect there to be, right? So lack of root pen or lack of root penetration. 2 straight edges, no weld metal. So we can see here we've got our 2 very defined edges coming down from our prep. Okay, so our root face hasn't been touched. Lack of pen. Okay, generally caused by too low of an amperage or too thick of a root face. Okay. Then we have lack of root fusion. So this is 1 straight edge. Normally occurring where we have misalignment of the plates. So if you're given a sample where you can see a high amount of linear misalignment, so the plates are physically stepped out from each other, have a look to see if you've got this defect. Okay, one straight edge. Okay, the next one is our root concavity. Couple of different ways that this can be caused. The one here looks like it's a high gas purge, but the point here is there's no straight edges. Okay, now when we put them together, we can look at it like this. So lack of pen, 2 straight edges. Lack of root fusion, 1 straight edge. Concavity, no straight edges. Yeah. If you mix this up, you will lose marks, right? Leon says, to add, I always look for lack of root fusion at the ends. Yeah, that's fair. Anywhere where we're going to come to the end of the welds and the weld is kind of let go and given up, especially if it's a test sample, right? If it's a qualification sample, he knows he's going to lose the first and last 25 mil, so you tend to give up at the ends. Yeah. But nail this, right? There's lots of marks potentially in your sample. Depending on what sample you get, you could have all 3 of these, which means there's a potential 6 marks, right? Gained or lost in this circumstance. Okay. Right. Okay then. So this is one I'm just going to put up, and we can all make comments, and if you're watching this video after, I would love to see you put your comments in the thing about what defect you think this is. This is an oddball one, which I think is quite an interesting output. You won't see anything like this in your exams, but it's a fun one to look. So have a think about it, come back and see what you can get from it. Okay, so what we've done there is just gone through the definitions of our defects, right? Now we can go back and have a look at how do we apply those definitions to an acceptance criteria on some test samples, right? But before we do that, I'm just going to have a look at the comments. So what we got, when was the last time I actually saw anything? So I've read that one, read that one. Oh, Chris, I took my course in Thailand last October. The training was amazing. I don't know the guys out in Southeast Asia. I've never actually had the pleasure of meeting them. When I used to teach, there was literally, it was just us from the UK. There was no other team. There was 3 of us. Me, David Page, who's now the sort of section manager for weld inspection, and God rest his soul, Martin Farven, who passed away a few years ago. But there was only us 3 doing pretty much the entire world, so I never got a chance to meet anybody. I'd love to get out there. Maybe when I'm back in Singapore or something, I'll have a jump across. I did find the plastic samples strange to inspect. Yeah, that's one of the big things, right? The plastic samples, don't let them put you off. But have in your mind that to make a sample plastic, the moulding has to be good enough to pick it up. So the defects are always quite large. Yeah, it's very, very rare you're going to get something that's really, really small, picked up very well and consistently. Great. Leah, I've done the exam last November. We had several pieces with poor stop starts in the root, which confused with lack of pen. Potentially it could be both, couldn't it? You could say, well, it's a lack of pen because it's a poor stop start, is maybe how I would look at it. Crossed all it, and automatically we crossed all acceptance criteria. Yeah. Oh, Dalam, you're great. Thank you very much. Can't say that. I appreciate it. I really do. Thank you very much. But yeah, okay. I'll get embarrassed if I talk about that, Ryan. It's a very good tip for the undercut. Okay. Oh, right. I can't remember which tips I said now. I've done the same during the exam. Put my nail in to check. Yeah. So always do that. Trust your gut. If it feels deep, right, it probably is. Then check the acceptance criteria and kind of decide how accurate do you need to be. If the acceptance criteria says anything over 0.5 mil is a reject, do you think it's more than 0.5 mil? It doesn't matter if it's 1 mil or 1.5 mil or 2 mil. Is it just more than 0.5 mil or more than a mil or whatever it's asking? Okay. So I read that one. Is there a chance of lack of concavity or root undercut throughout? So, Leon, do you mean is it they can be together? Or right, so you can't. So I'll break this up. I'll answer all versions of this question possibly. Yes, you can get root concavity. Yes, you can get root undercut. Root undercut is exactly the same as cap undercut, just on the root side. Tends to be more for plates and pipes that are welded in position. So if a plate is like in this position, you're more likely to get root undercut on the top. But coming together, no, right? I guess we could put them a bit like underfill. Where's my torch? Sorry, let me just put my torch back on here. If we look at this top bit of this sample, this area here is underfilled. I can feel it, it's down. But I can see I've got these funny edges left and right of it. Even though these are wavy edges here, right, this is an undercut, but this up here is undercut, right? This is just the wavy edge because the underfill has filled the groove and has melted the plate, but it hasn't undercut as such, yeah? So when we say undercut, we want to be right into the material. So I would separate them out. If you say it's concavity, it's only concavity, yeah? It won't be doubled up with another defect. Chris, arc strikes. I was carrying out some inspections last year and the heat treatment technician was arcing his connection wires, yeah, to a structural member. And yes. So this is always a thing when we use different processing methods around what we've done in welding. We do have a risk of arc strikes. MPI with prods is generally not accepted because it can cause arc strikes after heat treatments and stuff. Hopefully, depending on the heat treatment you're doing, you might be able to accept arc strikes at certain stages of the process because it's going to go through a normalizing, annealing, quenching, tempering type process. So for instance, if you're making castings, when you make the cast and you pull it out the mold, you could use prods and live with arc strikes. because you know it's going to be solution heat treated or annealed or something that's going to fix the grain structure in the arc strike and then be machining and all that type of stuff. But heat treatment and something maybe that's only like 600 degrees, so a stress relief, could cause an issue with the way they apply the contacts. Yeah, it's a thing. With marks within the heat effector zone, although lower heat connection, what is it? Did the heat treatment make a mistake? All right, so I think I might have answered that. I think, Chris, did I? The heat treatment, the connection of the contacts for heat treatment needs to be accounted for and needs to be thought through as a process. Sorry, pardon me. We have seen people screw this up and then cause hardened areas that aren't corrected. So yeah, got to play with that. Yeah, cool. Right, so we'll jump back to these. I think that was all the comments. Right, so just jumping back to the practical exam itself. What is the point of it, right? The only point of this exam is not to test if you think this weld is a pass or a fail. It's to say, can you identify defects and have them approved or rejected against a standard? Okay. Because at the same time, we give you any exam sample, you're going to say, yeah, it's a fail. Of course it is. It's awful, right? You're never going to get an exam sample which is completely defect-free, because that would defeat the point of what we're trying to do, okay? So, and we've already said our acceptance criteria, especially for CSWIP, is very much modelled around this 5817 standard, okay? So here is our 5817, our acceptance criteria as we stand. We're going to look through this. I don't know if this is big enough. Sorry, I'm just going to see if I can make the screen bigger. Should I zoom in a bit as well? Right. Hopefully that's bigger. I didn't realize how small it was going to be on the screen. I'll move myself right away over here to the side. Okay. Where was I? I've lost me trail of thought as I'm trying to read comments and that as well. So the acceptance criteria is kind of based out like this, okay? So you have a defect reference, so A to whatever, right? B, C, D, E, F, G. This is how our questions are going to be answered. So instead of having excess weld metal underfill on the boxes we're going to answer in, it's just going to be the reference, okay? So for every reference, we have a defect type. Oh, I'm gonna have to come out with this, aren't I? Right, the defect name. Our defect name here is what we're looking for. Yeah, everything we've just been through as the definition section. We've then got our comments, which are a description of what that defect is. So again, if you're worried and can't remember what a defect is, have a look at that, and you just need your reassurance. And then we've got our free acceptance categories, okay? So I've named them for my version of this. I've just called them level A, level B, level C, okay? It doesn't really matter what we call them. It's just 1, 2, or 3, yeah? Right. So we've got our acceptance criteria. We know everything we need to have. You can see here, I've missed out purposely the comment for undercut. Do we remember what our comment, how would we describe undercut? Right? Give me the 3 things that we need to take account of and where the defect is likely to occur. Okay. The winner wins the respect of the whole group, yeah, type of thing. There's no prize, okay. So what would we be looking for if we looked for undercut and we needed a statement in there? While you're answering that, Can I show you something cool? So I've just had delivered all of our course books that we give out during our course. So you'll get your own little book, carbon art book, which has a link to our a thing to our website and stuff like that. Everyone will get a pen. I'm still waiting on the pens, but I don't know. I was on Vistaprint, the website, and I got a bit carried away, so I did stickers. Oh, which way is that? For everyone. So when you come to one of our courses, you'll get all of this and, you know, everything like that. Some nice course books. The slides we're using today are the slides that we're going to be using for teaching, so they'll all be printed off nicely, and you'll have everything like that. So that's the plan. First courses run from March the 3rd, big major courses, which is going to be a little bit scary, but we'll get there. So what we got here, sharpness, depth, yeah, is it straight, not straight? Yeah, that's a good one. In the base material, yeah. So we've got all of them there, so that's what would be in there. So you say some word in like depth, depth and length, whatever. The which we've got in the acceptance criteria next to it. We've got 0.5 of a mil or there, but sharpness, no sharp indication, and we can go from there. Okay, cool. Right, so at the minute, everybody, I guess if you've done and you've seen content online and the way it's been built for years, I say years, since I did mine, God, in like 2002, whatever it was, 20 odd year ago, has been a plate. But today, it's not, right? What really they've done is they've taken the plates and they've cut them up into sections, right? So we've just sectioned them, and you're going to have 8 of these sections to look at. Okay, it's the same defects, it's the same way of doing it. It's just by having 8 of them, they can give you more variation in the exams and stuff like that. First point here is every section will be numbered in some way, right? Always make sure that the numbering system of the question you're on is the section you're looking at. I have seen people, I don't know, it says segment A, actually be looking at segment B. Okay? And when I'm in an exam and I'm the invigilator, I kind of tell you, I'm not allowed, right? There are really, really strict rules around what we're allowed to do as invigilators. So always make sure, first thing, question says segment A, I have segment A in my hand. Away we go. Okay? Right. Okay, so for each segment, we're going to get 3 questions. First question, what is on the sample? Second segment, would we accept it to class A? Third question, would we accept it to class C? So what we're saying is, what is there? Is there any defects rejectable to the highest category? Is there any defects acceptable to the lowest category? Right? There's ways of looking at this answer sheet which should help you be able to make these decisions. This is what we want to go through. Right. So here is our sheet. So we've got a defect references. So like I said, instead of saying excess weld, metal, undercut, blah blah blah, we just give them a letter. So for instance, A is undercut, cap height. Okay, excess weld, metal. Right. Then you've got your 3 questions. Now, if you're doing this on a tablet, which is what TWI are definitely pushing for at the minute, because there's more exam security and all that type of thing, the likelihood is each of these questions, 1, 2, and 3, will be on a different sheet, like on a different place. Has anybody seen that from who's already done the test? Oh, so like clockwork, Leon says exactly what I'm after. Thank you. The tablet was so annoying to use, so I took a sheet of paper. Exactly. That's my biggest tip with doing this exam. You have a note piece of paper. You can do any notes you want. You're not allowed to remove that paper from the exam, so it's just junk. It won't be marked, right? Write your answers down on that first, and then come back and fill in the tablet. You have more than enough time, okay? I promise you it will be enough time. You'll nail it really quickly, okay? So you've got that along here. Right, so we have our three things. We have our tablet, we have our segment. Again, I'll move myself out of the way here. We have a segment here, ready to inspect. We have our answer sheet along the bottom. And then we have our acceptance criteria. If you've got them three things on the table in front of you, we should be good, right? Next, we need to start inspecting our segment. So the way to do this, or the way I do it, start at the top of our acceptance criteria. First question, do you have excess weld metal? The answer is pretty much always going to be yes, isn't it? So if yes, we have excess weld metal, we have A, so we put a cross in the box, right? Do we have underfill? Have a look at it. What is underfill? Any point at which the material drops beneath the plate level. Use your fingers, feel it, run your hands over it, okay? I'm going to say I have underfill in my segment, so I'm going to put an X in the box. Yeah, so I've just see Leah's comment here. For me, it was uncomfortable to do the check on the samples because they're on the keychain. I agree. Having them all put together, it does make it a little bit more difficult. I've found like lying out the sample, like the keychain on the table, and just pulling out one individual one, and then trying to deal with that makes it a little bit easier. But I completely understand your frustration with that. Yeah. So we've got underfill. C, do we have any slag? I don't think we have any slag on this sample, so I'm just going to leave C blank. Then I can go to my next one, and my next one is undercut, which is D. I have undercut, so I have it there. So you see what I'm doing? I'm not trying to blindly inspect the whole segment in one go. I'm using the acceptance criteria to structure my answer and come down. Then I know I don't miss anything, right? And I can get to the end, I can get to defect M, knowing I have looked for every defect. And I don't have to panic. Oh my God, did I look for like a pen? Well, I must have, because I went down the acceptance criteria, okay? And we go from there. So that's what you're going to do. You're going to go through, and so then we're going to turn our sample over. So then I can say, right, I've got a stop-start. We can see where it's a stop-start disappears in. Let me zoom in on that. So you can see here, the stop-start kind of pulls in here. We've got potentially another defect there, so we might have to look at that in a little bit of view. So E is my stop-start. Mechanical damage, H. So mechanical damage, anything that you don't know what it is, but you know it's damage to the sample, okay? That's what we're looking for here. We've got our penetration, height. So we know we've got penetration, so we put an X in. Our lack of fusion, which is that bit we saw just before there. How do I know that's lack of fusion? Because I can see one straight line disappearing down there. Okay. Then K, so J, there's no lack of root pen, so I'll leave it blank. K, I've got my lack of fusion. There you go. L, burn through, no. Concavity, no. So there I've got my first set of question ones, which I'll go back here. Which imperfections are identifiable on the sample? So we found 1, 2, 3, 4, 5, 6, 7 defects, right? My next question. We've said we don't have any slag. So do I need to check that again? No. Yeah, I've said I don't know. So now I can speed up with the rest of my inspection because I only need to look at 7 defects. I don't have to look at A to M again, right? And we've done that relatively quickly by following our segment all the way down, right? Next question then, which imperfections are acceptable to level A? This is where we now need to do some measurements, okay? So what we're going to do, excess weld metal, I'm just going to measure it at 3.5 mil, right? I use my gauge, again, gauge video on the channel, check that, and then look at my acceptance criteria, okay? So looking at my acceptance criteria, we are saying, so again, I'll zoom in on this section. So A, excess weld metal, so excess metal above the plate, right? We're looking at level A, so I'm allowed a maximum of 2 mil, right? I've said I've got 3.5 mil, so an X is going to go in my box, yeah? Because I have found a defect which is not acceptable to class A or level A or whatever we want to call it, right? And I need to do the same. So underfill, right? Underfill, I've measured it being 4 millimeters long. It extends for 4 mil, right? What's my acceptance criteria? Again, come to my acceptance. Let's zoom in for C. So B, underfill, I reassure myself it's anything below the plate. Level A, not permitted. Great, nice, easy, don't need to think about it. If it's not permitted, it just gets across in the box, right? I don't need to do C. I can move to D, which is my undercut, yeah, which I'm going to measure it 0.8 millimeters deep, and I'm going to say it's sharp. So there we go. Again, level A, not permitted. Doesn't matter how deep it is. Let's just get rid of it, okay? So D, X in the box. Again, try to be structured like this. So what is it? Next month, it's my 15-year renewal for my 3.2 is up. But luckily it's just a it's just a CV renewal. It's like the 5-year version. But when I sit my practical exams like I did 5 years ago, this is exactly how I do it. Just work through, keep it going, keep it moving, okay? Right. Then I can come to the back side. So we'll need to look at E. Poor stop starts. Again, we think we've got a poor stop start in this area here, right? So poor stop start. Indications must be separated by 30 millimeters, right? That's what it's saying up here in my acceptance criteria for B. But I've only got one. So they're not separated from each other, are they? So I would say that I can accept that because there's only one defect. If I had 2 stop starts relatively close to each other, then I'd measure the distance and I'd go from there. So I'm going to leave out E and I'm not going to put an X in because I think it's acceptable. Then we're going to go mechanical damage. So mechanical damage again, zooming back in on here. No straight tack welds permitted. Parent material must be blended smoothly, and the depth, if I've caved it out, has to be a maximum of 0.5 mil. Right. So straight away, we can see a weld left, and I'm not allowed that. Therefore, it's a reject. Put an X in the box. Right. Penetration height. So I need to measure this. Okay. So I'm going to measure it at 3 mil. Again, I'm literally going to step through all of these, right? Come to it, penetration height, the max is 2 millimeters, but I've got 3 millimeters, therefore X in the box. And then I can miss J, because I've got no lack of pen, straight to K, lack of root fusion, right? It's not permitted, and I have it. I don't even have to measure it, okay? So, but I will, I'll say it's 1.5 mil, but it's non-permitted, X in the box, right? So you see the structure we've got here. We've got like question 1 has quite a lot of defects running across the top. Question 2 will either have the same amount of X's, but I think, looking at acceptance criteria in general, it'll actually be maybe slightly less X's in the box. So you can see we actually got 1 less because we accepted indication E, right? So when we then move to question 3, which is next, okay, how many X's are going to be in the boxes? Is there going to be more, less, or the same? Because now we're working to an acceptance criteria which is going to accept quite a lot more stuff, right? So there should be less, is my gut feel, okay? I don't know what exam you're going to get. I don't know what the sample's going to look like. But in logical thought, I can see a lot. Question 2, I'm going to reject a lot. Question 3, I'm going to reject less. So we should see this pyramid shape of defects coming down as we go. If you have more defects in question 3 than you have in question 2, you've done something wrong. Yeah, and we can look at it and we can fix it, right? If you're doing it on paper, like you're sketching it out yourself before you answer in your tablet, you should see that should be easy to see, hopefully. God, fingers crossed, yeah? So we can move through it. Now, I'm not going to go through level C to that extreme, but if you want, what I would say is replay this video, go back through it. When you get to this point, have a go at doing Class C with the measurements I've given. Okay, what do you think is acceptable and rejectable? And in the comments, I need comments for the algorithm. Stick in what you think the answers for free are, and then we'll have a discussion about it and see where we get to. Okay, right. So that is pretty much all of the practical and how we hit it. Now, let's have a quick my 5 top points, right? 5 things I think you should do in your exam. Okay. Number 1, start at the top of the acceptance criteria and make your way down. Just use that to gauge which defects matter. Then we can forget about all the other nonsense that's going on, right? Is it a bit of a porosity or isn't? Who cares? The acceptance criteria doesn't ask you, so just go and do something else. Yeah. Again, question 2: defects that are not in the acceptance criteria do not matter. Don't care how many you have, you're going to ignore it. Right. Number 3: if you forget what a defect is, read the comments. Yeah, the remark section. It is going to help you an awful lot. Right. People forget defects, right? Exams are stressful. Make them as easy as you can by using the information you have. Right? Like we said before, for tip 4, question 1 will have the most X's. Question 2 will have a little less. Question 3, probably a little less again. It's a good way of just cross-checking yourself, right? And if there is no X in question 1, you're not going to think about it anymore. Right? You don't need to look at it. Move on. Save your time. You have 8 segments to do. Okay, 8. Yeah. That time needs to be used productively, not rechecking things you've already checked. Okay? If you can hit them, generally think, if you can hit them 5 points, you're a long way there to making sure you can achieve the practical part of the exam. Okay, hope that's been of use to you this morning. Like I say, if you have any questions, ask them in the comments after this video, uploads fully. We should be good. I have to do a runner now. We've got a load of stuff we need to go and get done today, Saturday, very busy. But hopefully, yeah, hope that helps. Next Saturday session in 2 weeks' time will be all about the WPSs and the welder quals, and I want to go through them in the same way as we've done here. I'm going to try. I can't promise this, right? But what I want to do is release a free multi-choice for the WPSs, which we can then work through in the live stream. What I'm trying to do is work out how I get that out. I think I can, and I don't know. I think I can put it on our website just as a zero cost thing, which you can download. That'll probably be there next weekend, but definitely before the live session in 2 weeks' time. And then we can go through them like an exercise thing and have a look, right? Again, any questions, comments below. And with that, I'll hopefully see you again. Yeah, the community's still growing. That's awesome. Let's keep it going. Yeah. Have a nice weekend, guys. See you later.